Okay, so this is the question.
Question number 3, sir.
Yeah, question number 3. So can you tell me the graph which the
Graph
question
is,
number
sir, third graph, sir.
third graph? Yeah,
Yes,
so
sir.
the third graph is by making this is the third graph, I think. Yeah. So these are the vertices. Okay, so if you start coloring the vertices, so how will color? Suppose if you color with this one with the red. Okay, suppose you colored this vertex as a red, then you cannot color this vertex, and this vertex as a red, right?
Yes, sir.
You can color
The
this.
adjacent 3 vertices.
Yeah, adjacent vertices you cannot color with red, so but you can color this vertex. And if you
Yes,
once you color this vertex, you cannot color this one and this one.
yes, sir.
Now take another color, let's say green I am taking. So if you color with this one, you cannot color green with this, but you can color green with this vertex with green and this one also, or either any one of can choose.
Okay,
Now,
sir. Okay, sir.
if you choose
Got it, sir.
another color, then it will be, so there are
Yes, sir.
three
Yes.
colors left.
Yes, sir. 3 color. Okay, sir. Got it, sir. Thank you.
Yeah. Yeah. So next is Siddharth. Yeah, hi Siddharth.
Sir, I have doubt in activity 10.1, question number 4, last one.
10.1. Last one. So
Why option 4 is correct, sir?
1, 2, 3, 4. V4 is reachable from every node. Where is that V4? V4 is,
Third one, sir. V4 is reachable from V1, V2, and V5.
sorry. Oh, sorry. V1, V2, and V5. So this is V4. So V4 is saying to be reachable. So this is V1. So if you start with V1, this is our V1. So see that this is the both side you can go. So this is arrows are both sides. So you can go from here to here, and this arrow is from both side also. So that means you can go, you can reach V4 from V1. Is it fine?
Yes, sir.
Now if you check, the next one is V2. So V2 is also have both side arrow, and this one also have both side arrow. So from V2 also we can reach V4. Okay.
Sir, 4 one is also correct, right? From every node, V4 is reachable from every node.
No, so if you check with the if you check with the if you check with this vertex
Which one?
or this vertex, let's say V6. If you check with V6 is no, we have okay V3.
So bidirectional arrows.
This is bidirectional. This is
Sir,
you
from
start with
V8 it
V3,
is not
V3.
bidirectional. So from V8.
V8, V is this one, and yeah, here is the. If you
Yes.
start with the V1, this is one direction, and this is the vertex which is at V7. It is only in degree. If you see that in vertices are no, there is no out. Sorry, out edges. Only in edges are here. This is this one. You cannot go from here to here. So that's why you are unable to reach. If you start from V8 or even V7, you cannot reach to V4.
So we have to check from every node that
Yeah, as the option, this option is for every node, so you have to check with the every node. Okay.
Okay, sir. Sir, and what is undirected graph? So, right, sir? If these arrows are not present, then that graph.
Undirected mean, yeah, undirected means you can say undirected are nothing but the directed graph, but it is bi-directed. By it have both side direction. So as here, it will be like this, as you can see in this one, or this one. You can go to V1 to V0 and V0. So undirected means, so if you both side have this is bi-direction. So if both sides, so you can erase this one and say just simply this is undirected graph with two vertices and one edge.
Okay, thank you, sir.
Now next is I think Anuradha. Yeah, Anuradha.
Good evening, sir. Am I
Good
audible?
evening. Yeah, you are audible.
Sir, I'm facing problem in activity 10.2, question 4.
10.2. Yeah, the same just now I discussed the last one, I think. No, this is the question 4.
So what is the procedure to solve this?
So this question is what is the, like, the independent set?
Yes, sir.
What is the independent set in a graph?
Sir, the set of all vertices that are not connected.
That are not that is not connected, that is not joined with a single edge, means one edge. So if you have a graph, let's say this one, so independent set in this graph, let's say this is V1, this is V2, this is V3. So independent set in this graph is, as you can say, choose V1. So you cannot choose V2, it will be V3.
Yes.
Okay, so two vertices can not be joined with a vertex. So whatever you are take, this is the subset of the set of vertices. So whatever you take the subset, any two vertex will not join with the single edge. So that is called the independent set. Now in this problem, what are the vertices? What is the nodes or this vertex? What is denoting this vertex or node?
Sir, different teams.
No, nodes are, what is that? A graph is created where the nodes are the events. Nodes representing the events, not the groups. Nodes representing the events and edges representing the sports, connected pairs of sports. So edges represent the sport, which says that if it is, let me show you. So in this problem, let's say that I have make it this smaller thing with that. So this represent, or any vertex represent the event. Okay, these represent the event. This represent the event, and this edge represent the sport, and it represent the sport, which says that this event, whatever the sport event, and this, let me read it out. So represent the edge, these edges represent the sports where the team share the member. So this edge represent, if suppose this is the event and this is the event.
Yes, sir.
So in between these two events here, mean to say the sports, the better say two sports. What is that? A graph is created where the nodes are the events and the edges. So your college has sent a sport team for the festival. The team is multi-talented and each have take part more than one. Okay, so can be part of the team, two different sports. Okay. Okay, this is the event actually. And yeah, each event, the what is the, suppose at this event, suppose football used to play at this event, the hockey, the team is playing the hockey at this, in this event, this is happening the football match. Okay.
Yes.
And this is for, let's say, hockey. And this is saying to be the, whatever the team is here and whatever the team is here, sharing the members. That's the mean. If it is there is no member sharing the member, then you will not, like here. Suppose this is kabaddi. Okay, this is kabaddi. So no member here is there is no edge. That means there is no member in between these events or in this sports sharing the member. So football, no player of the football, like no one of football player will play this kabaddi, and any like no kabaddi player will play football. So that's why there is no age. But if there is a age, then the sharing members are there. That's the meaning here. That's the problem. Now, this is the problem we have. This is the graph we have. Now the question is, if the college want the team members should take part in the maximum number of sports. So how, like the college wants, like we want to choose. So we have to find the, we want the team members to take part in maximum number. We want to find the maximum number of sports. So here mean to event means as you started said the sport, it said the sports. So actually events, in that events, the sports is happening. So the college wants maximum number of sports or event can happen so that the maximum that member can take part in that
Yes.
sports here, take part. So how will they maximize? So I want to maximize the number of sport like events in that player can play. So can you now let's back to our options here. Independent set we know. Now minimum size vertex cover. You know what is the vertex cover?
Yes, sir.
Vertex cover is what?
Sir, it is the set of all vertices
Mhm.
which can cover every edge, but the minimum number of that.
Minimum number of that. You want to choose those vertices which cover the most of the edges.
Yes.
So
Sir, not
So-
all edges, that is not required.
that is not required. That is called perfect. No, perfect matching is that. The cover is, vertex cover is we want to cover those minimum number. Yeah, minimum number is we want the minimum number of vertex which cover the all edges. Like is in the the CCTV cameras. Suppose in this graph. Suppose this is V1, V2, V3, V4. So you want vertex. What will be the vertex for? That is a subset of vertices which cover where you set up the CCTV camera. Suppose this is the intersection point of the corridor. So where we put the camera so that it will cover this edges.
Sir, V2.
So V2 will be. So vertex cover, you will say this one. The minimum vertex cover. Either you can put here separately, but that we want minimum. That means we have to put here.
Yes.
That's the meaning here, minimum vertex cover. Right? So if we want, so is this our question? We want to minimize or maximize? Or what is our problem here? We want to maximize.
Right, sir.
But what is it saying? This minimize the vertex.
Yes.
So it will not solve this problem.
Yes, sir. No, sir.
This is the thing which independent set is actually related to the vertex, and this is the to maximize the independent set.
Okay.
That's why this option is going to solve that problem. And also the independent says that independent set, if you choose this one, then you cannot choose this one. So, and yeah, if two buddies playing the same two different sport, suppose some persons are playing to different sport, one person is playing. So if he is playing here, then he is unable to play here. So that event is not possible to conduct this one. If it is he playing this one. But we want to maximize it. So I have to choose this one.
Yes, sir.
That's why the independent set will work. Maximum independent set will work to solve that problem.
Okay.
Is
sir.
it clear?
So, sir,
Hmm.
for minimal coloring, sir, we can start with any vertex.
So yeah, you can start with any vertex, and see that is that giving the minimum number of colors? Minimum number of colors is possible or not?
Okay. Right. Thank you.
Maybe there is a possibility that there are 5 colors will enough, but we want the minimum number of color which suffices to color the vertex,
Yes, sir.
the vertices.
Yes.
Okay.
Thank you.
Yeah. So let me see the next one. Okay. So anyone have doubt? Or now the last day we discussed with the till breadth first, till lecture 4 we discussed. Still remain to depth first search, and we introduced something like just given to what is the depth first search. We did the brief thing on. Okay, and we'll see the head complexity and the DAG and topological sorting we'll see today. So anyone have doubt, please let me know. Otherwise, we'll start with the same as we did for yesterday session, which is
Sir?
held on morning. Yeah.
Can you please take the question from question number 5 from practice assignment?
Yeah, okay. Okay, so yeah, I will take your question first. Let me take with the Sunita. Sunita is okay. Okay, otherwise let me take with your, then we'll go to with the Sunita's problem or doubt. Activity.
Practice assignment, question 5.
There is no link. Okay. Question number 5. This one. I don't know where she went. Where she went? Yeah. Karishing. So is this question 5th question?
Yes, sir.
Okay. So what's your doubt here?
Sir, I'm not able to find the minimum vertex cover. Like I am able to find maximum independent set. Minimum vertex cover, like how to proceed with it.
So here is the maximum independent set, and V suffix C is the minimum vertex cover. So okay. So from you can start from any vertex. No, let's say if you are starting with this one. Okay, we'll see that how we want to maximize the independent set also. We have to choose such vertices which will maximize to make the independent. So let me. So this is the graph here we have. And these are the vertices. And this is we have. Okay, so let's say this is V1, this is V2, this is V3 and V4. V5, this is V6, this is V7, this is V8. So there are 8 vertices. So we want to maximize the independent set from this graph. So you have to try to avoid those vertices which cover the maximum number of edges. So you have to choose such vertex which have the minimum number of. To start the independent set, we have to choose such vertex which have minimum degree. If it is a maximum degree, then it will cover the most of the vertex. No, so we have to most of the vertices. So we have to choose such a vertex which have, let's say, minimum degree between the graph. So suppose each have the three degree, I think, no? Okay, this one.
Yes,
So you
sir. All have 3.
all have 3. So I think you can start from any vertex. So let's assume I started with this one. Let's say this is V3. Okay, so I chooses V3. So I cannot choose V1, V5 and V4. Okay, but I can choose V8. Okay, so once you chooses V8, okay, then you cannot choose V7, V1 and V2. So you can start with choosing like this, so that like you already chooses V1. Like once you chooses V3, you started with V3, you cannot choose V1, but you can choose V8. So adjacent of the V1 you can choose, like which is the near to V1. So let's say you can choose V8. Once you chooses V8, you cannot choose V5, V7. Okay. So so then you can choose the adjacent of, let's say now here you can choose the adjacent V2. Okay, as this is the adjacent to V7. So once you chooses V7, sorry, V2, then you cannot, it is already attached with the V7. You cannot choose V4, but you can choose V6. Okay. Now, this is the set. This is a subset of vertices. Now, if you choose any one of the vertex from this graph, okay, if you choose any one of the vertex, what will happen? Let's say let's say you chooses V1. Once you chooses V1, it will connect with the V3. So you cannot choose. If you choose V2 is already in that. If you choose V7 is connected with V2. So you cannot. So if you choose V6 is here already. If you choose V4, so it's already connected with V6. If you choose V5, then it's already connected with the V3. That means the only possibility that this is the only independent set. If any other vertices you are choosing, surely there is a connection in between two vertices. So what is the answer for this one? For Vi, it will be 4.
Sir, it's 4.
So yeah, okay, this is V4. So are you getting know how to choose or how we'll get the independent,
Yes,
maximum
sir. Yes, sir.
independent? See, this one is also independent set. V3 and V8. This is also independent set. But we want to maximize. We want to choose such vertices which give the maximum independent set. Is it clear?
Yes, sir.
Now for vertex cover. Now vertex cover, we want the minimum vertex cover. So we have to choose such vertices. You should to start with those vertices or those vertex which have maximum number of degree, so that we can minimize the vertices, no? Number of vertices. So but each have the same as here. Each have the same vertex. Each have the same vertex have the same degree. So then you have only option that you can start with the any vertex. Let's say you started with V1. Okay, you chooses first V1. So if you chooses V1, vertex V1, then this one is done, this one is done, and this one is done. 3 edges have done. Vertex cover means what? We have to choose such vertex which cover most of the edges. And we want to minimize. We have to minimize the number of vertices. Right? So I have now from here I have to choose such vertex which cover the maximum number of edges. So if I choose this one, because if you choose this one, then it's already covered with the V1. So you should not choose this one. You should to choose this one or this one. So assume that I chooses V5 now. So it's covered this one, and this one. 3 edges have covered now. Now, what we need to choose? If I choose this one, then it's already covered this one. So I should to choose this one. So let's assume I chooses V4. So it cover this one, and this one. Okay. Now, which one I should to choose so that it cover the.
V7.
So if you choose V7, then it will cover this one, and this one. Then this V7. So this is the Vi, and this is going to be Vc, right? What is the answer for this one? Because this is the minimum number of. Maybe if you choose any one of the rest of any other, because each have the degree t, so I don't think this is going to the minimum.
Yes, sir, it's 4.
It's 4, right?
Yeah.
So whenever you start choosing for minimum cover, you have to choose such vertices which have the most degree, which have the maximum degree of the vertex. From there you should to start, so that you can choose. If you choose that vertex, is which cover the most of the edges. That's why you want the minimum number of cover. No, that minimum you want to cover the most of the edges. That's the vertex cover. Is it clear?
Yes, sir, yes, sir, I got it.
Let me see the next one, who is Sunita is want to ask something. Yeah, Sunita. You are not audible. I think she is not here. Anuradha. Anuradha.
Hello, sir. Am I audible?
Yeah, you are audible.
Sir, I have a doubt again in this practice assignment, only question 2.
Question number 2.
Yes.
Okay. Question number 2 is this one. Okay. Okay. So what's your doubt here?
In this one, in actually the graph is here, but in question number 4, sorry, I'm getting the answer as 7. See, the question is if Joe wants to have a party at his house. So then, sir, I calculated the number of nodes, the number of vertices which can reach Joe's house.
Just
Then I got the answer 7. But the answer is 8. So do I have to include Joe also?
okay. Let's see that. Okay, what is that? Joe wants to have a party. So then at most how many members can join the party? Yeah, so you have to include that, because at Joe house, Joe is one person, no? So it's asking how many person, how many members. So you have to include Joe also.
Okay, sir. And sir, in 10.8 activity,
Okay, this
sir,
one.
how do we solve this? What is the procedure?
So see, if you have this number of vertices, so what is your varying of the edges, no? If you watch the lecture, you can, if you have n number of edges, vertices, n number of vertices. Okay, if you have n number of, let's say, cardinality of, this is the vertices, set of vertices, which is n number of vertices. So then possible number of edges, how many possible number of edges can be there?
N into n minus 1.
N into n minus 1 by 2, right? And this is, if we want the connected, so it should be greater than n minus 1, right? Your edges will vary from this to this. I think I'm missing something. Let me see once. You can say from here, it is already given in the starting that how many possibility there. Yeah, the above bounded above thing I know. The lesser one is, I think, let me see, let's verify it. I think it is n minus 1. No, yeah. So this is from C, that if you want a connected, if G is connected, M can vary. M is the number of edges or the cardinality of the edge set. Can vary from n minus 1 to n into n minus 1 by 2. This is the variation.
So I think I did the wrong one because I thought it was from n square to n into n minus 1.
So n square is the at most, like that is the case for that is the n square is for the case that maybe now the edges, if you draw the edges for the n square, then edges can intersect.
Okay, okay. Okay.
For
so
that
not
is the
in the
case.
graph.
Yeah, maybe then you will get not for the planar graph.
Okay, okay. And sir, one more last note, sir. In activity question 10.7, sir.
Okay, okay, Sunita. Yeah, I can see. Yeah, I see that Sunita is missing. So 10.7.
Yes, sir.
Which question number?
Sir,
This is one.
Sir,
So,
CF is a forward edge in this one. But
so,
the answer is saying it's wrong.
so do you know what is forward edge, backward edge, and cross edge?
Yes, sir. For
What is forward edge?
For forward edge from U to V,
Hmm.
the pre-post numbers of U will include pre-post numbers of V.
Okay. Yes. Yeah. And what is backward edge?
So for backward edge, the pre-post numbers of V will include pre-post numbers of U.
Okay. And what is the cross edge?
For cross edge, the pre and post numbers of both the vertices are disconnected.
Okay. Yeah, disjoint. Yeah. So if you in the graph, so is there any main property that the forward or backward or cross edge have some specific property that is that edge will be the part of the tree or not, DFS tree or not?
No, sir.
So if you are talking about the forward, backward edge, cross edge, then it will be never part of the DFS tree.
Yes,
Yeah.
sir.
If it is a part of DFS tree, then that you will not talk about, you are not going to talk about the forward. That is, you will never say that is forward, backward, or any.
So
of.
we call it tree edge, right?
So yeah, that is a tree edge. So in that case, we'll call it as a tree edge, not backward, forward, or cross edge. So backward, forward, or cross edge, those edges will never be tree edges. Okay. Now, if you have this one, you have graph this one. So start if you want to find the DFS tree, first find the DFS tree. What is going to be the DFS tree?
Sir, A to B.
A, B, C, F, and D.
Yes, sir.
This is going to be your DFS tree,
Yes, sir.
right? Now which edge is left? This one and this one.
Yes.
BD and AC is these two edges left.
Yes.
And these are edges not the part of the DFS tree.
Yes. Sir.
So you can talk about only these two edges, forward edge, and you can say now these two are either forward or backward or cross edge.
Okay. Okay.
Getting no? Now hope you get the answer.
Okay. Yes, sir. Thank you.
Yeah. Sunita is asking for AQ 10.1 question number 3. Okay. So in this question, which one is going to be the graph? So in this question, there is one thing we need to be very clear that while drawing the graph, this resistance, or register, or sorry, resistor. Resistor is going to your edge. Okay. And this, whatever the wires are there, these are going to your vertices. So this thing you have to note here. What is here? Resistors, sorry, yeah, or either resistors is equivalent to nodes. So equivalent to two nodes connected with one edge. So this resistor is going to your edge between two nodes. So if you draw the graph of this one, how it will be? So see that you have this one. This is the resistor. Here is, then here, and this is here. Now here. So see that this is one edge, this is one edge, this is one edge, and these are the nodes. So let's say this is the nodes here. This present this node. Let me erase it now. So this is going to be your node. This is going to be your node, and this is the whole this one part is going to be your node, and this resistor is going to your vertices. Sorry, edges. So this is your first edge. This is your connecting this. Take this is and this is. Now, if you one thing you can do. Now this is the graph, corresponding graph for this circuit. Now that means your resistor is going to be your edges. So see that if you draw the graph for this one, how many edges are here? Anyone can unmute or tell how many edges can possible with the same logic? Anyone can unmute and tell that how many edges?
5 edges.
So
Why?
6.
See, the resistor are going to be the number of edges. If there is 3 resistor, that means there is 3 edge. So how many edges now from on this?
Six.
So 6 edges going to be, right? 1 edge, second edge, third edge, 4, 5, 6. 6 edges is going to be in the graph. So this is one trick you have. So we don't know how the exactly graph will be, but it is going to be complicated to draw, but you have some idea that it have 6 edges. How many vertex can be? 1 vertex, 2 vertex, 3 vertex, okay, 4 vertex. This is the whole, this wire is going to be your vertex, and this resistor is going to be your edge. 4, and this is I think 5. Or let me count it again. This is 1, or not only 1, this one till this one is going to be 1 edge. So better, sorry, vertex. So better, so let's count what we have. The edge will enough, I think, to count the which one is going to represent, to neglect the option. So which vertex, which graph have the 5 edge, 6 edge?
A. Sorry.
1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, this have 6. This have 1, 2, 3, 3, 4, 5. This have 5. Okay, this have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This have 5 also. We want 6 edges, no? 6. We want 6 edges. So this is not going to be this one. The first one have the 6 edge. 1, 2, 3, 4, 5, 6. Only the first one have 6 edge. Otherwise, the rest of 3 graph will don't have the 6 edge. That means the only option is going to be the correct graph, the representation of the graph, that representing the graph. Is it clear? This is the way you can use. So anyone else have doubt? Okay, Sunita is done, I think. Okay. So let's start with our, which last time we did. So if you watch the last lecture which held on yesterday morning, so we reached to the breadth first search. Breadth first search is nothing but a kind of, let me give an idea.
Sir, sorry to interrupt.
Yeah.
Sir, I did not get the notification for last lecture. Like you are saying, there was a lecture on Saturday, right?
No, not this yesterday. Not Saturday, sorry, yesterday morning.
Okay, sir, I did not get any like a notification on WhatsApp or
No, it is
email.
in the calendar itself because each session has shifted. Saturday session is shifted to, I think, Tuesday, or I think Saturday session is shifted to today's session. Friday session shifted to morning. So there is a shift in the session only because of the quiz.
Yeah, okay.
And
Actually, sir,
we,
I get the WhatsApp message like if there any class. So I did not get for that one.
no, so in the calendar it is available. You can watch in the YouTube. This is the morning session. Solvitas is its name with the Solvitas, but it is not the Solvitas, it is just activity. And this is the YouTube link, you can watch it.
Okay, sir. Okay, thank you.
And also I will suggest you to watch the older session also if you have. You can watch the old session also. I will try to give an announcement and you can watch the old sessions. That is also nice sessions are there. Okay. Well, in announcement, we'll send the link of each last sessions video, the last term session video. Okay. So so let me start with the breadth first search is, suppose you have a graph. In the breadth first search, you have a what is the process? You first search whatever you have options. So first of all, why these are the algorithm we needed, with first search or depth first search. So most probably to analyze the graph is we needed to analyze the graph. We have this breadth first search and depth first search, means reachability, connectedness, path, walks. So these are, or is there any cycle, directed graph, in a directed or undirected graph. To analyze a graph, we needed this kind of algorithm, breadth first search or depth first search, BFS, TFS. So in the BFS, what is that? Suppose you have a graph with, let's say, this is the graph. Okay, this is, suppose this is the graph. Let's say this is V1, this is V2, this is V3, this is V4, this is V5, 6, this is V7 you have. Okay. Now we want to check either we are able to reach from V1 to V5 or not. That's the thing. So if you want to check, while this is, see, you are able to see that, okay, we are able to reach via this observing this graph. But suppose you have 1,000 number of vertices and very big graph, then how we'll check that? So this is an algorithm, BFS, which tells you can code it in the Python. You can made a code of that and give the conditions as, or algorithm as the BFS, and you can easily say that if it is reachable, then you can say, yeah, this is true, you are able to reach from V1 to V5. If it is not, then it will return to false. So this BFS is an algorithm to check is that you are able to reach from one vertex to another vertex. So let's say I want to check whether let's say from V3, I'm saying, let's say I want to check from V3, I'm able to reach V5 or not. So what is the VFS says? Whatever just start from here. So you have 2 ways to go. So you can list them. So like mean to say, here as if you see the algorithm, so there are visited and queues are here. So these are the queues, let's say, and these are V1, V2, V3, V4. These are till V7. You have some saying to be is it visited or not? So no or not. So not. So if you started from V3, so you have 2 ways. So once you have 2 ways, you can list them in this queue. So let's say in the order wise you want to list either V4 or V2. So let's say this is V2 and V4. You listed in the queue. Now take V2 because take V2. So this queue is for the explore. When you started exploring, you can remove that. So let's say you started exploring V2. Okay. From V1 to V3, you started V2. Okay. So once you started, then you should to erase it and give it the how many vertex you are able to see that. You are able to see V1. Okay. You are able to see V4. Okay. You are able to see V7. Okay. Okay. This is not the way. It will become here. Okay. So let me erase it here. Now, so once you reach, we start exploring V2. So from here you can visit, you are able to see V1. You are able to visit V7. We have V4 already with the V3. Because of V3 we have already V4. I just erased it just now, but you have already V4 with the because of V3, and V5 you have. So here should be V4, and rest from here it will be started because the queue says first in last out. What is that? Yeah, no, first in first out. That is the VFS. So let me again write here. This is V1, this is V4 we have already, and V7, V5, V3 already we have done. We have visited that. We have already explored. From V3 we reach V2. Now you have this one V2. Sorry. So now explore V2. From V2, let's say now you have V1, no? So just erase. So no, now you have to check V4 because this we are in queue. So now we need to explore V4 once you started exploring V4. Okay. So you need to erase it, and this will come here. This is become V1, this is become V7, and this will become V5. Okay. Now if you started exploring V4, then you are able to say the V2 is already explored and V3 is already explored. So you from here now you are unable to reach anywhere. You can just okay, you are, that's all. Now again you have to back, and you whatever from V2 you have already visited. So from V2 you have visited, now V1. You need to explore now V1. So you start exploring again V1. Now you need to erase it. So mean to say this is a process, no? This is a process. This is the process here. This is the process. Now you start exploring, you are enabled now from V1, you have only V2 which have already explored. So now again from V7, let's start exploring V5. I have just given V7 here, but if you write in alphabetic or in the in a proper order, so let's say now here V5. So you start exploring V5 you have. So which you want to check the reachability. So yeah, you can say yeah, we are able to reach V5. So this is a process this is a algorithm to check we are able to reach from V3 to V5 or not. So whatever you have ways, you can do this. But so see, this is the means whenever you start exploring VFS, see, you from here you can go 2 ways. So in Q, you have to write those two ways, those vertices where we can start and choose any one of them. If I choose this one, then from here start exploring and then reaches to here, then again start exploring, because this have many ways. So in a list, this is the queue. In this queue, you just list them, because via mouth you forget them. So that's why you just list them, and one by one, if you are unable to reach that point, if you reach that point, that's all. If you are unable to reach, like you first started this one, then you found that, okay, no, I am unable to, from here I am unable to go, not able to go anywhere. So back to the, let's check the another route. That's the BFS. But now what is DFS? DFS says, this is again, oh, I erased it. This is another strategy, and this is very similar to the, as you used to do in the internet searching. Very simple example. Suppose you want to search a book, okay, in internet. What you will do? You will just go to Google and type. So if somebody says search book 5, there you can find the many books somebody suggested you. So what you will do? You will type in Google book fee. That is called book fee. If you search that, you will get that the book, many books, mathematical books are, or any kind of engineering, science, arts books are there. So if you search in the Google, so there are many threads will show. From there, you will pick. So from here in the Google, you give the, okay. So there are many ways it shows. There are many threads have given here. So suppose you chooses this thread and you start exploring this one. So you start exploring. Once you started exploring, it give many thread here. So you chooses this thread now and start exploring the book name. And suppose there are many books with this thread, but you are unable to find that. Okay, so you are here in any one of the book and find that, okay, there is no book. So you will back to here, and from here, okay, from here you will go to another, because this is the list. You will check another thread and start exploring again that thread. If it is there, fine. If it is not there, then back. So you search the all thread and you are unable to find. So from here, now you will back to here and start exploring the other thread. So this is DFS, the same thing, the DFS. Whenever you have a link, just go in, search there. If it is not, just back to the same link. And if it is again search, if there is another link, just go to the another link and search inside there, go to there inside. If it is not there, just back. And from here, just go to another link and search there. If you are able to find that, that's fine. If it is not, then just back. This is exactly DFS. But if in BFS, you just remember the roots. Just remember the roots and one by one search. But what is the DFS? You have one thread, just go in. If you are able to find, that's good. If you are unable, just go back and check another. This is the DFS. This is the differences in BFS and DFS. Is it clear? Am I audible?
Yes, sir.
So is it clear DFS, what is DFS, and what is this DFS and what is BFS?
Yes.
This is exactly
sir.
the algorithm. And if you see
Yes,
the
sir.
algorithm, it is written in the systematic way. Just make a list here. And this is V1, V2, V3. And in place of Q, there is a stack. And what is that? See, what is in that? Whatever you explore the vertex, no, from that stack, you just erase that and back to the rest. So just see carefully. This is the exactly way to do the DFS. So we can see here, from here, our graph will check. We will do that this DFS from here. We want to check the reachability from V5 to, sorry, V3 to, is that vertex V5 we are able to reach or not. So how we'll do that? So let's say now I started from V3. Okay. So I have two ways. Just I chooses this thread, this path I have chosen, this edge I have chooses. I have two edges, but I chooses this edge and reach to V2. Okay. From V2, there are many way, but I chooses V1 and reached V1. Now from here, there is no vertex. So what I will do, I will back to our V2. And again from here, I will choose another vertex. I will choose another edge. So suppose I chooses, because from B2 this edge is also there. So let's say I chooses this one now and start exploring it. So when I started exploring, I reach here. Okay. So now again from here, I can go this side, because this is the way, but it's already explored here. So again I have to back. I have to back here again V2. Now I chooses this one, this thread, this edge, and start exploring. So I reach here and start exploring. I reach here and start exploring. I reach here. Suppose there is another edge here, and badly I chooses this edge and start exploring. But I thought maybe there is no next vertex is here. Then I have to back here. Okay, and start exploring again here. So okay, I reached to finally V5. Then you can say there is a path, or there is a way we can reach V5. So from directly here, once I started this one, I chooses this edge, start exploring via this edge. Then we easily we reached, but we don't know. So that's the depth first search. Once you chooses this thread, you start going in. If it is there, then fine. If it is not there, then backtrack, and again next choose the next thread. The same thing is here. This is the DFS. Sorry. So these two algorithms are there, DFS and BFS. The next one is, I think now, that is called depth first search. Now this depth first search create a tree, which is called DFS tree. And with first search, BFS also used to create tree, which is called BFS tree. If you see that, the DFS is actually what is that? Last in, first out. What is that? DFS is last in, first out, which is going to be the last come. We just not last in, last out. No. This last in and first out.
First in,
Sorry?
last.
First in, last.
No, sir, it's last in, first out.
Last
DFS.
in, first out.
Yes,
For
sir.
DFS, it is last in. Say what is here, from here itself you can say it came in the last. See, if you start exploring from here, or in the stack, it is clear who came the last. From here you can remove that. In last who came, you can start removing and to reach here. So who his came last, he will out first. Who came the last, out first. So that's why the last in, first out it is. So now if you have this graph, if you want to make a tree of DFS tree, how it will be. So from V3 we started. So this is V3. Okay, from V3 we reach V2, and V2 we first go V1 and then backtrack here. So from here we again backtrack to here, and then we reached V4 here. This is V3, this is V2, this is V1. From here we first check V4 here. This is going to be V4. From V4, which seen that already we have visited. So we are not going to explore V3 because we have already explored V4. Then backtrack to here, and then what we did, we start exploring V7 vertex. This is V7 and then V6. So let's say this is V8 here. So this is going to be V7, this is V6, and this is started here V8, and then again backtrack and reach to V5. So this is going to be your DFS tree. So there are some question on DFS tree. As here the first, if you see that this question. Suppose we perform DFS on this graph. So that when we visit a vertex, we explore its unvisited neighborhoods. So whenever if we start DFS from, let's say, E is here as in this. So whenever there is a neighbor, okay, these two are the neighbor of this vertex. So suppose we choose this neighbor, then start exploring. This is the DFS, and this have 3 neighbors. So I choose this neighbor, then start exploring this neighbor and go ahead. This is the thing here. We explore its unvisited neighbor in a random order. Which of the following could represent the edges explored by DFS starting at the vertex C? That means in this question, we want to find the DFS tree. So if you, let's see that how we'll start it. So in this DFS is started from the vertex E, as this question is here. So we started from here. So let's say I started from here and moved to this B. And once we started this B, this is going to be here and this is going to be here. And we cannot, this is not going to be your edge, as because we have already visited, we have already explored B. This is going to be your this side. And once we have here, we cannot go this side because we have already explored it. Then again start backtracking from here to here to here. And from here, we have already this one, we have explored this one, but we didn't explore this one. So from here to we reach here and start exploring this. So from here, there are 3 ways. We have already explored E because we have started from E. Then we started either G or D. So let's say I started from G and then D. So which graph is going to show this one? As here, this one, we started E, then B, and then no, there is, then we did for this one. So is there any connection? So
option A.
Option A have the same. Started E, B, then F, A, then backtrack, then again back to C, and then G, and then D. So this is going to be your DFS tree. Okay, so this is the depth first search. Now there are some example, or what is that? The next is application of DFS and BFS. What is in this lecture? In this lecture, thing to be the application. So what are the application? So using DFS or BFS, you have checked that is that graph is connected or not. Anyone, if you either any one of the algorithm you are going to use, it's tell to you, it is going to tell you, is this connected or not? If it is not connected, so there is a component. So what is that? So suppose you have a graph. Let's say I'm making this one. Okay. So suppose you have this graph. Let's say this is V1, this is V2, V3, V4, V5, V6, and V7. Okay. Suppose you have this graph. So I want to check. So somebody said that is vertex V7 is reachable from V2 or not? This is the question. So if this is the question, somebody's asked if V7 is reachable from V2 or not. From here, we are able to reach V7 or not. So what we can do, any one of the algorithm we can use, either BFS or DFS. Once you have once you started DFS or BFS, so as you know, if you let's say I use DFS, so I started exploring From VFS, I started to this way, I started going this way, and then after this way, and it stopped here. Then backtrack, and here again reach and started with this way, and again stopped here. That means we are unable to reach V7. So what is the DFS actually gives now here is this graph is not connected. This is the use now you can say. This is the now VFS DFS is going to analyze, as here analyzing is this graph is connected or not. The question is this. So yeah, then you can say using the DFS or even the BFS also, you can say this graph is not connected. So this is the strategy. This two strategy used to tell that it is going to be connected or not. Once you have that this graph is not connected, so we can now the DFS and VFS also tells you the component number. It gives the components, how many components are there. The number of component number, there is one word component number. So if you give them the component number, it will give the number of component in the graph. So suppose I have, as I started from here, okay, V2, and I have seen that it is unable to, we are unable to reach V7. So let's say I just given this, let's say I am saying the word component number 2 as, let's say I just given V2 as 0. And from V2, wherever you are able to reach, these are all under the V2, sorry, under the V2. So I just given this number 0. From V2, I are able to reach V1, V3, and V5. Okay, this is the TFS and VFS will help. Now, unable to reach V5, any one of this side of vertex. So I just given this vertex now V5, 2 as 1. Okay, from V5, we are able to reach, we are able to reach V6 and V7. This DFS, and if you do start DFS, VFS, this gives you that, okay. So these are all the vertices are under the 1. You just give the number 1 under the V5. So these numbers you can say the component number. So it have 2 component. Suppose there is another vertex V8. So from V5 you are unable to reach or either V2, from you are unable to reach V8. Then again you start you from V5 your DFS and VFS. And okay, you are once you started, it's ended automatically that there is no other vertex, there is no neighborhood. Then it is you can give the number 3. So this is going to be the component number for V8. So you now you can say there are 3 components. So these are the component in a graph. So what is the DFS and VFS helps that? It tells you the graph is connected or not, and also give the components, how many components are there in a graph. Is it clear? I don't know.
Yes, sir.
Audible? Okay, so this is your this is the thing DFS and VFS tells you.
Sir, we call these two like separately components, right? We
Yeah,
don't call them branches.
No, these are the components. No, these are the components in a graph. Component 0, component 1, component. So, sorry, I gave here 2, 3. No, this is 2, 0, 1, 2. So component 3, sorry, component 2. This is component 1, and this is component 0. So there are 3 components.
Okay.
Anything is, yeah. It tells you also the graph is cyclic or not. So what do you mean by the cyclic graph? And also tells you the tree. Let's see that from here. It tells you the what is TFS tree and what is forest and what is tree here. So whenever you have you have already know the this 2 algorithm VFS and DFS. This tells you that in a graph is connected or not. It also tells you the component number and give the number of in a graph how many components are there. In this graph they have 3 components. Now it tells you the BFS and DFS also tells you the is this graph is uh, is this graph is have the cycle or not? What do you mean by cycle? So suppose you have a graph. Let's say this one. So this is V1, this is V2, this is V3, and this is V4. So if you start DFS or VFS, any one of the, so this is undirected graph. First, let's say this is undirected graph. So if you start DFS or VFS, it tells you that this graph have cycle or not. So as here, you started, let's say this, you started VFS from V1. So you'll started here. So you'll start exploring this one once you visited this one, and from V1 you are able to visit V2 and start exploring V2. You started exploring V2. This is, let's say this is V4 vertex, and reach to V4 and start exploring V4. So one by one you started exploring. Sorry, this is V5. Let's say this is V5. Exploring V4. Once you started this V4 exploring V4, then you reached V3, and then once you reaches V3, then you have already see that there is an edge which connected with V5, adjacent with the V5. So that means this gives you a cycle. So once you so see that this because of the, when you started exploring V3, you see that you have already explored V5. So it tells you that this graph have a cycle or not. So this is your cycle. Okay. So this is the application. You can say this is all under the application of graph. And there is one word, tree. So what is tree? Tree is a graph. So tree is a graph which doesn't contain any cycle. So this graph have a cycle. So this is not a tree. So a graph which don't have cycle, or a graph which is acyclic. Acyclic means there is no cycle. That graph doesn't have any cycle. Then that graph is actually a tree. So like there's a tree, as we started saying, to with this DFS tree. This one. So this graph doesn't have any cycle. So in a tree, there is one property. In a graph, if you have n vertices, okay, and you are saying this graph is a tree, then it have exactly n minus 1 edges. If it is a graph which have n vertices, and you are saying that graph is a tree, then it have exactly n minus h. Yeah, sorry, n minus 1 edges. Neither it cannot be less than 1. It cannot be less than n minus 1. If it is less than n minus 1, then it will become disconnected. These are the property of a tree. And if it is greater than n minus 1, then surely there will be a cycle. So if there is a tree, it is saying, it is a fact that it have n minus 1 edges. So we have already done this, the DFS tree. There is a pre-post number and the forward and backward edges.
Sir?
Yeah.
So I want to confirm something, like for undirected graphs, all non-tree edges are form cycles, right?
Only backward.
No, sir, for undirected graphs.
For
all
undirect.
non-tree edges.
Yeah, non-tree edges. Yes.
Yeah,
Is
all
going to
non-tree
form-
edges, right?
Yeah.
And for directed one, we have to decide it is forward, backward, or cross. Then
No,
we have
so
to check
if it is there
backward.
is a backward edge, then surely it will have a cycle. The
Yes, sir.
backward edges is the responsible for in a directed graph. Backward edge is the responsible for is their graph have a cycle or not.
Yes, sir. Yes, sir. That's what I want to confirm. Like for undirected one, we don't have to check all these things. We just have to check non-tree edges, and all tree non edges will form cycle. But for directed graphs, we like have to check. It should be a back edge. Only then
Yeah.
it will form cycle,
Yeah,
right?
yeah. But yeah, yes.
Okay, okay. Okay, thank you, sir.
So the next thing is application in application of BFS and DFS. The second application is I think it's give a path also. So directed cycles are there. So what do you mean by this? So this is again the same to be the finding the pre and post number. So from here it is started backward and forward edges. We have done with this. So okay. So yeah, we have already did with the pre and post number. Once you started from here and started increasing, these are the numbers. So pre and post, if you say that generally there is you can use that definition. The best definition is just say that if you have a graph, then which one is going to be forward edge and which one is going to be backward edge. It's from the graph itself you can see these edges are not going to be a tree edges. Okay, and directly mean to say it in the bigger interval, the forward edges will be a sub interval of the bigger interval. So this is for telling backward and forward edge. We just now discussed already via the question. Okay, now next is the strongly connected and components and strongly connected. So that means there is a connectivity with the direct graph. So what is the strongly connected means? If what do you mean by the strongly connected means? Suppose you have a, let's say, I and J. Okay, let's say this is K and this is L. Sorry, this is. So these are the vertices. Let's say Vi, Vj, Vk, and VL, and now he's here. Okay, now this is here, and this is another one is here. So strongly connected means two vertices are said to be strongly connected. Okay, let me make another thing. Let's say this is an edge. Okay, this is an edge. So strongly connected means you will say the two vertices Vi and Vj, sorry Vk, you will say strongly connected. These two vertices are strongly connected if there is an edge. Let's say this is an edge, directed edge if you are saying. So this is an edge, and there is another edge which is connecting to the. If you go with this way, from if you are going with the directed graph in a directed graph, you are able to reach from Vi to Vk, and you are return back with this now with the not same edge. You are unable to return with this different edge as here. So in such case, you will say that Vi and Vj are strongly connected, as you see in the video. So vertices I and J, I just said Vi and Vj, or I in our case Vk is there. Vertices Vi and Vk or Vj are strongly connected if there is a path from I to J and a path from J to I. So not only edge, I was talking about edge only, no? So it's talking about that there is a path. So let's say there is an edge here. Here to here now. So this is a path now from Vi to Vk, and this is another path. So if you're able to go from Vi to Vk with this path and from return back with another path, so you can say these two vertices are strongly connected. If in a graph, this is true for each pair of vertices, not only one, as this is the case for only one. But if it is true for each pair of vertices, then you will say that graph is strongly connected component. That portion, if it is graph, a strongly connected graph. Otherwise, it is in connected with the component wise, then you can say strongly connected components are there. Now have started the summary. Now the complexity we are not going to discuss, because complexity means to be the time proportional. Like these are two algorithms. So which one takes the more time even compared to like which BFS takes the more time or DFS. So BFS is generally, if you see that, is easily can be done on adjacency matrix. And if you do with the adjacency list, so this is in this question, if you see that this is the complexity says which is going to be the minimum time or which is going to be the maximum time, or which algorithm you are going to use that which takes a more time even compare of less in compare with another algorithm, or when you are using on the adjacency matrix or on the adjacency list. So okay, you are going to apply in a DFS or BFS on adjacency list or in adjacency matrix, or whatever you are going to do. So which algorithm give the minimum time or maximum time? So this is the complexity you need to check. Like if you do with the adjacency list, so it give the overall time proportional to the number of vertices and edges. But if you do with the number adjacency matrix, then that is the time is overall time is proportional to the number of n square, which is if you graph have n vertices, then the time is proportional to n square. So these are the complexity. If you watch this lecture, it will slowly introduce that this is totally for, if you see, this is will help you in the graph theory generally, sorry, in the Python programming, the time proportional when you do the DDSA course. But it tells you what is, there is one definition, sum of the degree. So if you have m edges in a graph, if you have m edges, the sum of degree is 2m. And what is the sum of degree? Sum of degree mean to say an edge is connected with the two vertices. So that's the word. If you have m edges, then it helps sum of the degree is 2m. Okay, so why this sum of degree? What do you mean? The degree of vertex is there, and there is another word, sum of degrees. So if a graph, let's say if you have a graph, okay, let's say you have a graph which have m edges, then the question is what is the sum of the degrees? Yes, we will just directly say 2m. As here you can see. What do you mean by this? So sum of degree means sum is, why this is 2m, degree of a vertex is I, the number of one is in a row. Okay, So you can remember this word as a sum of a degree. Okay, if you have m edges, then you can direct the question will be, if there is question, then you will just directly ask that. Like if I'm making a question that suppose you have the question is like this. Suppose G is a graph, or not only graph, G is a tree. Let's say G is a graph, which is tree, which have, let's say G is a tree, which have 5 vertices. Then question is find the sum of degrees. What is the answer for this one? What is going to be the answer for this question? Anyone can unmute yourself and tell. Am I audible?
Is it 6?
6. Why you are thinking 6? I just said G is a graph which is a tree and it have 5 vertices. G is a graph of 5 vertices which is a tree. Then find the sum of degrees. Sum of degree is a word, no? Sum of degrees have m edges, then it have sum of degree is 2m. So what is the sum of degree for this graph?
2 into 5, 10.
10. But m is for edges, not for vertices. Now tell me. This m is a vertices, no? This is the number of vertices. But the sum of degree is for the edges. So what is the sum of degree now?
20.
Sorry?
There will be 10 edges for 5 vertices. So 10 edges.
No, can you remember with the word tree? The graph is a tree.
Yes, sir.
So in a tree, if it have 5 vertices, so how many edges can be it have? Exactly how many edges will have? It will have. It will have.
It will have minimum 5 edges will be there.
No,
I don't
if we
remember.
have suppose my question is, I am saying if there is a graph which have 5 vertices, okay, and that graph is a tree, then how many edges that graph have? I just now said the
5 edges
property of
only, sir.
trees. I just now said the property of tree,
No,
right?
sir, I just joined actually.
Oh, so anyone who is here can tell what are the property of a tree? Yeah, or what is the fact number 1, or you can say what is the property of a tree? If there is a tree with the n vertices, then it have exactly n minus 1 edges. Just now here I have just wrote, no? If I have a tree which have n vertices,
Yes, sir.
then
To say, sir.
it have
Correct.
exactly n minus 1 edges.
Yes.
Correct?
Yes.
That means if G is a graph with the 5 vertices, then it have 4 edges.
Four edges.
If now this graph have 4 edges, then what is the sum of degree?
8.
2 into 4, which is
8.
8. The sum of degree of this graph, which is a tree, is 8. That's all. Which is with the help of this one, we will count the number of edges, and from the edges you can count the sum of degree. Clear?
Yes. Yes.
This sum of degree means what? Suppose you have a graph, let's say, let me explain that word also. Sum of degree is what? Suppose you have a graph, okay, this one. Let's say this one. So what is the degree of, let's say this is V1, this is V2, this is V3, this is V4, this is V5. What is the degree for this vertex V1? What is the degree of the vertex V1? 2. What is the degree of vertex V2?
2.
2. For this,
3,
3. For this one,
2,
2.
for this one,
3.
3. So how many degrees now if you just count this? 2 plus 2, 4, 4, 3, 7,
12.
7, 2, 9, 9, 3, 12. See that? 12,
Yes.
right? So total degree, sum of the degree means here the total degree is just, this is the total, that's the word uses, sum of degrees. This is 12. So either you can count with this one or just count the edges now. 1, 2, 3, 4, 5. Oh, so
6.
one is missing, 6.
6.
So there are 6 edges. So now as we have formula 2m, m is 6 edges, 6 edges, so 2 into 6 is 12. Is it clear? Is it clear what is the sum of degrees? Means the number of the total degrees of the vertices. Just sum them. That is the sum of degree. Either you can use this one, or if you have number of edges, directly you can count that. And also multiply with the 2 and you'll get the sum of degrees. That's the here sum of degrees. Now is it clear? Except to the
Yes,
remember
yes.
this, you
Yes,
just remember the what is the word here, sum of degree.
Right, sir.
Okay, now let's move to the next thing is the last one is the directed acyclic graph. So what is the directed acyclic graph? Okay. So directed acyclic, cyclic means cyclic means there is a cycle in the graph. Acyclic means there is no cycle in the graph. So suppose if you have a graph which is directed graph, let's say this is the, okay. Let's say this is V1, this is V2, this is V3, this is V4, this is V5, and this is V6. Okay. Suppose this is a graph. Now, is this graph have a cycle?
No,
if
sir.
there is no
Sir.
cycle. There is no cycle. If suppose this is the case here, you go with this one, okay. Let's say I'm making this one. This one. So suppose the graph is this one. And see, this is the directed graph. And if you go with this one, this and this, it have a cycle. So this is not a directed acyclic graph. It have a cycle. Acyclic means it doesn't have a cycle. But here is the case is it have a cycle. So this is not a directed acyclic graph. Let's see if you erase this is a graph which don't have a cycle. So this is a this is a direct acyclic graph. This is the one thing. Now it have a good property, like if you have a directed acyclic graph, so there is a one best use actually. There is a one there is one use for as in this online degree you are. So for doing MLF course, or you want to register for the diploma course, and you have MLF you want to do. So either you just clear the diploma and the diploma entry exam, or if you are going with the starting foundation, Okay. If you're starting with the foundation, then if you want to do the course MLF, you have to do you have to do Math 1, Stat 1, Maths 2, Stat 2. At least these two courses you have to do. Or another word in also there is another thing, if you want to do Maths 2, then you have to certainly do Maths 1. Without doing Maths 1, you are not permitted to do Maths 2. So these are the dependencies. If you change with the dependency with the direction. So let's say I'm saying this is MLF course. Okay. So here is Maths 2 course, and here is Maths 1 course, and here is, let's say, Stat 1, and this is Stat 2. Okay. Okay. So doing Maths 1, there is no thing. Just you have to pass out with the 10, I think, or 12. What is the minimum criteria? You can check that. But there is no constraint on doing any course. There is no prerequisite. If you register for this online degree course, this BS degree course, you just started with the Math 1 or the other, whatever the combination you are going to take. So if you want to register Maths 2 course, there is a prerequisite that you have to done with the Maths 2. So before doing Maths 1, you cannot do Maths 2. So you can connect with this property. You can say that there is a dependency on Maths 2. So without doing Maths 1, you cannot do Maths 2. So this dependency you can notate with the direction. Okay. So there is no connection with the Maths 1 and Stat 1. Maths 1 is totally independent and Stat 1 is totally independent. Okay. There is no connection. There is no dependency in the Maths 1 and Stat 1. Similarly, in the Stat 2, there is a dependency that without doing Stat 1, you cannot do Stat 2. Okay. And now here is MLF. So without doing these two, you cannot do MLF. So there is a dependency on the MLF. So this dependency we change with this direction. Now this problem, whatever we just said, the context here, it's changed in a graph now. Now, if you see that this is not a acyclic graph. This is a directed acyclic graph. There is no cycle in this graph. This is a directed acyclic graph. Okay. Now, if there is such graphs you have, then if you have such graph, okay, such graph, so somebody says in which order, suppose some student came and asked that, then what I should to do, like which courses I need to choose here. We need to choose which courses, so that there will be no dependencies will happen. There will be no dependencies occur. Means there is no problem. There will be no problem. You can freely can do. Okay. So how will choose the courses from this? How somebody is asking for suggestions? How will choose this? So to choose,
graph.
So if you want to choose such, so that means you want to sort out the courses here. How you will sort out means you are going to choose. How you will choose that? That means you have to sort out. So sorting out these things is called a topological sorting. Means if you asked with some other senior guy, or itself you just messaged, you mailed in the support team and asked which courses I need to choose, or there is already used to the orientation. As you know, used to happen the orientation session, and there is used to the questions are there. You can directly ask there which courses I need to choose. So the suggestion you can say that is sorting. You are sorting. It suggested that just do the Maths 1 Stat 1 first, so that you are able to do Maths 2 Stat 2. So in which order I will do this? That is called topological sorting. There is another example you can say. like this is one example. Like now the next thing is doing MLP. MLP without I think you cannot do. I don't know what is the dependency that MLP and MLT is there some courses. Without doing MLF, you cannot do MLT and MLP. So this is the dependency. So suppose you have a graph and somebody is asking that how we'll sort out this. So how we'll do this so that is called topological sorting. Like I want to sort out like how I will choose these courses. That is called the topological sorting. So see, to do this, so to do this sorting, what we can do, we have to choose that vertex. So topological sorting means I want to sort out this S1, maths1, maths2 means these vertices. These are the vertices we have. So we have the set of vertices, which is M1, M2, MLF, MLT. These are the set of vertices we have. Okay, we have this is the set of vertices, and we want to sort out this in a proper way so that will be no dependencies. We can easily do this course. So how will or in which process I need to choose the courses so that smoothly I can finish within the time limit. That is called topological sorting. So to start the topological sorting, like which one I will start. So first thing if you see that in a topological sorting, surely, so there is a fact. If you see in the lecture, there is a fact that in a directed acyclic graph, there would be a vertex which have 0 degree, 0 degree, sorry, 0
Zero in
degree.
degree.
In degree, that is called in degree. Yeah, in degree, that is called in degree. It have a vertex which have 0 in degree. As here, in degree means, see that it have, so like here, the in degree for this M2 vertex is 1. But here the in degree vertex is 0. The out degree of this vertex is 1 because it have a going to out. Where the edge is going out. So there is a fact in the DAG that there would be a vertex which have 0 in degree. At least one. But we have already 2. Okay. So if you want to topological, some suggestion on how will choose the courses. So choose the first 0 degree in degree. 0, that vertex which have 0 in degree. Okay. So if you chooses M1 here, okay. Once you chooses M1 here, so now the topological sorting is actually an algorithm. If you see that it is an algorithm. Once you chooses M1, it have degree C. It have in degree. From in degree, it will be topological sorting because dependency C. Dependency tells you that the in degree, because as you see that S2 is dependent on S1. So in degree of S2 is 1. So in degree is actually just count those. Like for in degree, this is 0 for this vertex. In degree for this vertex is 1. In degree of this vertex is 2. In degree for S1 is 0. Okay. So in degree for this vertex is 1. And in degree for this one is, I think for doing this MLT or MLP, there is one needed Python. And for doing Python, there is one CT. Okay. So that's the one thing. Let's for till this for these courses we are doing. So for MLT, the in degree for MLT is 1. Okay. Now, once you chooses here as we started topological sorting, that is an algorithm. I chooses M1 because it have degree 0, in degree is 0. Now erase this one. Once you erase this one, okay. Once I erases this one, so is now the in degree of the vertex M2 is 0. Now it will become in degree vertex of M2 is 0. So either you can choose M2 or you can choose S1 also. Okay. S1 is totally independent. So I just chooses, let's say in the continue with the process, I chooses M2 now. Vertex M2. Okay. Now once it chooses M2, the in degree of MLS, once I choose this, now erase it. Now the in degree of MLF is become, previously it was 1, now it will become 1. So you cannot choose this because the degree of MLF is still 1. Now which one have degree 0? S1 have degree in degree 0. Okay. Now you can choose S1. Once you chooses S1, so just erase it. Am I audible?
Voice is breaking, sir.
Am I audible?
Yes, sir. Now it is clear, sir, but it was breaking, the voice was breaking.
Am I audible? Don't know.
Yes, sir.
you
Yes,
are.
sir.
Yeah, that's the, I thought maybe I got message, so that's why I'm asking. Okay. So, okay. Now you can choose S1 because it have degree 0. Once you erase it, now the degree of S2 become 0. It was previously 1, now it will come 0. Now we can sort it here S2. Once it sorted S2, now we can erase this one. Now the degree of MLS become 0. Now you can choose MLF. In degree of MLT become, it was previously 1, now becomes 0. Now this MLT is 1. So this is the, in a graph, it have so many topological sorting. Either you can choose M1, then S1, or S1, then M1, or before doing M2, you can choose S1 also, then M2. Like this, whatever the process you can choose. So for a graph, for a DAG, there are many ways you can do topological sorting, but this is a topological sorting of the vertices. Okay, that's all for the week 10 we had. This is the topological sorting. In order to choose, like how we will choose how the work we will start, so that we can finish the work without any classing or without any dependencies. How we can choose which work we can do, like here which courses we can choose, so that there is no class or there is no problem, and within the time we are able to finish that. So this is like, so somebody suggested do like this, choose the courses like this. Choose first maths 1 and then do maths 2, and then choose stat 1, then do stat 2, then do MLF and then MLT. So in order to proceed this is, suppose this is the whole online degree, BS degree. In this much courses you need to do this in this BS, not BS, this is the BS have the many courses. For the small course, for this MLF or foundation course, so this is the process you can take to finish the course.
This is one of the way we can sort.
This is the one of the sorting the courses. That is called topological sorting. There could be M1 S1.
Yeah, that also is a possibility. So
Yeah, there is
how
another
we will
way.
choose which is the best one, or how to cross check it?
No, so there is no best one. Only just we want to sort out. So are we able to finish the course within the time limit or not? That's the thing. Which one is going to best? Best, it is not the problem. We want to finish the course within the time limit. So what is in which way I will sort out the vertices? In which way I will choose the courses so that I can able to finish the course? That's the thing. That's our problem. That's our main
start
goal.
with 0 in degree, what is node, and then continue like that.
continue, erase and erase. Once you erase that edge, the next vertex in degree become reduce. It will reduce one, and once it will be reduced, now from there choose the 0 degree in degree, which vertex have 0 in degree, and put in that order. So topological sorting is a sequence. It's saying to be you are ordering a sequence, the vertices, which is the dependent with respect to the dependency, to reduce the dependency without affecting them. Now, if you watch the lecture, it will be very much clear to you what is topological sorting.
Yes, sir. Yes.
That's all for today. Now it is 10 also. Please let me know, anyone have doubt?
We'll go through the lecture once again sir, in the next session.
Yeah, just now hope you go through the lecture. Now you'll get the idea what is happening. And I think tomorrow is Thursday, and the next day after tomorrow is the last day of the week 10 credits. So we ready with that also. If you watch these two lecture, these two session, and maybe we will ask the lecture now, then we'll get the idea to solve the problems.
Yes, sir. In this idea
Hello,
we
sir.
can solve.
Yeah.
Hello, sir. I have a question.
Sorry, Malia.
Sir,
Your voice is breaking. Your voice is breaking. I'm unable to hear. Your voice is not clear for me. I don't know it is for all of you or for me only.
No, sir, it is breaking, sir, for everyone.
Okay.
We could not hear what we should.
Okay. So,
Sir,
yeah. No, still
No,
your voice is
no.
breaking.
okay.
Okay. So can we close the session now? Because we have done almost 10. And
Yes,
if
sir.
you have doubt, please let me know, because now I have one by one within 2 lectures, I finished the concept one by one. And I started with the path, walk, reachability, then one by one, what is the next thing is, then in the lecture wise, it was path. In the first lecture, what is graph? Then the coloring of the graph, minimum vertex cover, or independent set. And then in the representation, what is path, walk, reachability. And the next is the algorithms are there, BFS and DFS, which is nothing but to analyze the graph. And there are some application. In application, we have seen that graph is the DFS and VFS tells you that the graph is connected or not, components we studied, and how to make a trees, we gone through that very quickly. And the second application and the complexity we did in the second application with the same. I just told you it tells you the tree also is telling about the tree. And then complexity, we just know this complexity is just to know on the adjacency matrix and on the list, which once you apply the DFS and BFS on the adjacency list or adjacency matrix, which keeps the minimum time, or which one is time proportional to, like, which will take the more time or less time, because DFS and BFS are an algorithm, no? When you're doing on the adjacency list or adjacency matrix, which will take more time, which will take less time. That's here in the complexity, we'll see that. And in the next one, we just now we see the DAG, which is nothing but the directed acyclic graph. Acyclic mean to say there is no cycle in the graph. And there is one the best use to do this for the dependency of the work. We have seen with an example where is the dependency is happening, can change the dependency in a directed thing, and there you can see. And next is the topological sorting, which is nothing but writing the sequence of the vertices in an order from the DAG itself, directed acyclic graph, so that means in that order, so that their dependency will not occur while choosing your vertices. These are in this week. The next week we have longest pass in the DAG also. The DAG will continue. Topological sorting will continue with the topological sorting. DAG will continue with the longest path. Then there is shortest path. These two things we'll see in the next week. Thank you so much for joining. Anyone have doubt, please let me know, or now we can close the session. I don't know why it is very less participants these days.
Hello,
How
sir.
was the, yeah, hi. I think now, yeah, Malaya is
can you-
audible. Yeah.
Yes, sir. I have a question regarding the calendar. So in my this site, I cannot see the the classes of this mathematics. I can see the routine of the English and the CT, but this whatever you have shown, no, that I cannot find. Sir,
Now,
in my
can you refresh
calendar.
the page now? No, just refresh the page because of on Tuesday it was updated. I think on Monday or Tuesday it was updated. Maybe if you refresh the page, now it will show. First, this is done on the course calendar itself. If you will click here, where is that? If I will click here, it will show in the course calendar itself. Where is that course calendar? I think here. Where is that calendar? I think here. Click here to view the specific calendar. Click here to join. What is this? Yeah, this is the calendar. In the calendar itself, it will show.
But I have seen, sir, I cannot find these things there. And moreover, whenever I know I get this information regarding the class, through the WhatsApp message only. Regarding yesterday's class, I didn't get any message, sir.
Oh, but from our
They
side,
have
it
to
is.
add to the calendar, so from the screen just you have shown. From there, if you add calendar, then it will be shown, like how CT and other subjects she has added English. He has to add maths also to her calendar. Maybe after
Yeah,
that,
it is in the math portal. It is a calendar. No, this is a calendar link.
yes. If you link on that, it will get automatically added to her.
Yeah, it is in the calendar. So the whatever the time schedule of the sessions, it's already in here. See that this is the open which is going on today. It is there.
Okay,
So just check from here. So just log out and log in the portal. Because
Okay.
this is in Maths 1 calendar. This I don't think there is a problem. And students are used to join. I don't think it is a problem. For with the everyone, maybe with the specifically with you it is happening. So just log in and log out or refresh the page, will update it. So tomorrow is one session with the Solve with Us session, which will
Sir,
happen
at
on
what time?
that is same with 8 p.m.
Okay, sir. Thank you, sir.
Thank you so much. Good night to all of you.
Yes.
Thank you, sir.